Yes, and good evening, ladies and gentlemen. And even I saw some boys and girls, so good evening to you too. It's very good news. As Martin said, I've been given the honor to welcome all of you as Deputy Ambassador of the Netherlands Embassy here in London, and it's an honor. I must also say that as a diplomat with a law degree, I'm a little bit out of my comfort zone and intimidated by all of you around here, and especially the two speakers, I think. But in preparation, I visited the Science Museum this Sunday with my 5-year-old daughter, and we had a very good look at the mathematics exhibition, which is very impressive for those of you who haven't seen it, but I'm sure you all went. So please consider me to be fully informed. The embassy is excited to work with a partner which has over 200 years of experiencing in, as it says here, harnessing science for the maximum benefit of society. That's its mission statement, or part of it. And I wanted to thank you for cooperating with us, and especially you, Martin, for doing this with us. And this is, as you said, only the first in a series of lectures that we're hope to run for this year. And the close cooperation between us and this institute is a reflection, we think, of the very close relationship that we have between our two countries in general, the UK and the Netherlands, and science in particular. As close North Sea neighbors, the UK and Netherlands have inspired each other for centuries in this domain. As seafaring nations, both of us, sometimes at war, sometimes the UK won and sometimes we did, or actually a little bit more often than the other way around. We both relied on telescopes for navigation of ships, and hence we both excelled at studying the largest things, so the galaxy, telescopes, as well as the smallest of things, microscopes. And as early as the 17th century, microscopy pioneers, oh gosh, such as Robert Hooke and Antony van Leeuwenhoek shared their findings in academic publications. And some of these works and exchange of ideas are actually exhibited outside. And for those of you who haven't done so already, I would recommend highly to see the beautiful things that are on exhibition here outside of us. And one book is actually even the beginning of the topic that we're discussing, I just learned, the double-slit experiment. Don't ask me what it was exactly, but something with light and 2 tunnels, yeah. That's as far as it gets. But it's certainly, and that I would like to emphasize, it's not only in the past that we had close cooperation. These links and interactions carry on today between Dutch and British scientists and engineers. They're plentiful and they're productive. And we have no doubt that this close cooperation will also continue in the future. And we are still working both on the largest of things as well as on the smallest of things. And just to give you an example, joint work, for example, is going on the design of the Square Kilometre Array telescope, which is meant to study the very largest of things. And on the very smallest of things, the quantum realm enjoys the interest of both our scientific communities. And I think we're going to learn more about that today. These early scientists, such as Van Hoek and Leeuwenhoek, probably had no idea of the vast implications of their discovery, but we have since learned that science and technology can, of course, transform society. And I hope that our speakers might shine some light on this tonight. I am looking forward to undoubtedly 2 very inspiring speakers, Professor Harry Buurman and Professor Artur Ekert, but I leave it to you, Mr. Bal, to introduce them to the audience. Thank you again for coming tonight, and I hope you will all have a wonderful evening. Thank you.
Thanks very much. Let's just see if I've got the first of these. Ah, I have. There we go. There's a quantum computer. Until perhaps just a couple of years ago, I used to consider it my duty as a science writer to try to temper the hype around quantum computing by advising how limited they might be and saying, you know, you're not going to get your quantum laptop anytime soon. And that remains true. And of course, it's still, I still have a duty to debunk the hype. But I've been genuinely amazed at how this field has progressed just very recently, really just over the last 2 or 3 years. And I'm not alone in that. In fact, some people working in the field, I'm quite sure, have been taken by surprise at the pace of the change. When IBM announced in 2016, for example, that it had made this quantum computer with 5 quantum bits, or qubits as they're called, and that it was making this resource available as a cloud-based resource that anyone could register, any of you could register and use. It wasn't just a publicity stunt. You can do real science on this device. And in fact, 60,000 people worldwide have registered to use what is today slightly sort of cumbersomely called the IBM Q experience. And hundreds of papers have been written on the basis of work done on this machine. So it's a real resource for science. I was lucky enough last September to get to go to the IBM labs in Zurich. And this, if I can get it to move on, this is what I saw. There we go. Yeah, well, this actually is the interface. This is, you can just look this up online. This is the interface for the IBM's Q experience, that you just sort of plan out your quantum circuit and use it. But this is really what I wanted to show you, if we're going to get there. You wait until we have quantum technologies like this. They're going to go wrong in new ways. But this is what I saw, and this is one of these devices. And it's this room-filling device. And I'm nervous to use this now, but it took me back to the days when computers used to look like this. Now, I'm not quite old enough to remember that, but I'm certainly old enough to remember mainframe computers that filled entire rooms. And it made me think, well, if this is where we are now with quantum computing, where are we going to be in 20 or 30 years? Now, if you have any sense of the number of bits in the average laptop, probably of the order of billions, then 5 qubits might sound pretty pitiful. But therein lies the power and the promise of quantum computing, because by using bits that are governed by the laws of quantum mechanics, rather than the classical rules that just allow every bit a binary 1 or a 0 state, this leads to a potential vast boost in computing power and speed. And it also allows you to do things that you simply can't do with classical computers. In fact, that promise, more than the speed up, was what led Richard Feynman in 1982 to first suggest the idea of doing computing using quantum rules. Things are still moving on at a tremendous pace, and in fact, just last week, we heard the announcement of this next device, keep you in suspense, which is produced by Google. So it's not all IBM by any means, and Google are in this game. And this is their quantum chip, which for some reason they've called bristlecone, and it has 72 qubits, which is considerably more than the 50 or so that some researchers think is what was needed to reach a point slightly ominously called quantum supremacy, when quantum computers become capable of things that classical ones can't do. So it sounds as though the future has suddenly arrived. But of course, it's never as simple as that. For one thing, there are big questions about how far you can continue to scale up these quantum computers, and in particular, how to handle the errors that inevitably arise when you're doing a computation, because the fundamental laws of quantum mechanics prevent you from dealing with errors in the same way as we do for classical computers. And it's one thing to create a prototype device like this, but of course another thing to find a niche in such a well-developed industry as the classical computer business. So what are the real prospects for quantum computers? We have here tonight 2 speakers who are perfectly placed to give us some answers to that question. When, back in the 1990s, quantum information technologies were still just a speculative idea, in fact, he just called it earlier on a family game in those days, Artur Ekert was one of the key movers who drove the field forward and sustained the notion that it was really onto something. And Artur is based at Oxford University, where his invention of a form of quantum cryptography in 1991 triggered an explosion of efforts worldwide. And he's contributed to many important advances both in the foundations and in the experimental realisations of quantum communication and quantum computation. I think it's fair to say, I hope this isn't unfair, that the Netherlands, we don't always think of it as a vast hub of activity in computer technology, but it has become one of the most active countries in quantum information technologies. And some of that is thanks to our second speaker, Harry Berman. Harry built the quantum computing group at the Centre for Mathematics and Informatics in Amsterdam, the first, in fact, in the Netherlands to work on quantum information processing. And his research focuses on quantum computing and algorithms and complexity theory. And he's developed a kind of complex systems approach to thinking about quantum computing, things like how to make the best of distributed quantum resources. Harry has a background in computer science, and he's looking at the vital question of how to develop algorithms that we desperately need to actually do anything with the resources that quantum computers are offering. So I'm going to hand over to the two of them, who will speak for about 30 minutes, and then we will open up the questions, and I'm sure there will be plenty of questions to you. So thank you very much. And first of all, please welcome Artur Ekert.
Thank you for this introduction. I don't really feel like a prophet to be able to answer all your questions, but in preparation for this particular talk, I was thinking what and how I should present this subject, because there's probably 125 ways to talk about quantum computing. And then I concluded that perhaps the best approach would be to tell you where this extra power for quantum computing is coming from. And that of course will take us to quantum physics, and I will have to explain a little bit which part of quantum physics is responsible for this what we believe is an extra power in quantum computing. I will have some equations, for which I apologize, but those of you who are familiar with probability and complex number will probably find it quite easy. Those of you who are not, well, don't worry too much about it, because you can just skip all those equations and hopefully you'll follow the gist of the idea that there's something new there. As Philip mentioned, that about in the early 90s, this field was a family business. So Harry and I met in early 90s, and it was at one of those meetings where we were discussing the nature of randomness, and somehow someone had the idea that, well, maybe quantum has something to say about it, and gradually talking about ideas that I always thought it was just completely blue sky research. I never ever thought at the time that it will ever be the case that someone from commercial world or banking sector will come to me and start talking about investing in this field. But here we are today, so one never knows. Okay, so before I tell you about quantum theory, let me start with probability. Now I have to just mastermind this classical technology first, obviously. Just let's see how it goes. Here we are. So. And usually when I give lectures in Oxford to my students, I usually like to start with giving them a little bit of a historical background. And I honestly think if there's one person that is basically responsible, in a way, for mathematical tools that we use today in quantum physics, is this guy. It's Girolamo Cardano is his name. There's, by the way, a very nice books written by Michael Brooks that appeared recently about his life. And so this person, in the 16th century, came up with mathematical foundation for two basic tools that we use in quantum physics. First, it is probability theory. And if you think it was all done in France, that's not quite true, actually. He was about 100 years earlier than Pascal and others. It's just simply that he didn't publish it at that time. So his work on probability was written down and was published a bit later. And he was also the first person who spotted complex numbers. So he was, in his work on trying to sort of find a solution to cubic equations, he noticed that there's this weird thing like the square root of -1. Actually, he was, to be more precise, was square root of -15 for some reason that he was interested in. And he thought, well, you know, this is weird, it's wacky, and it's not clear what to do. It's probably completely useless and irrelevant. And even, in his book, Ars Magna, he called those numbers, strange and probably absolutely useless, but you can operate with them, if you just assume that you can take the square root of -1 is a symbol, so you can be very instrumental and try to play with it. So here we are. We have two tools, complex numbers, which is basically like any numbers, but every now and then, the square root of -1 appears and we write it as I. Unless you're old-fashioned engineers, then you write it as J. Then the probability is another thing, and of course, his interest in probability was mostly because of gambling, and he was quite a gambling scholar, a fascinating character, by the way. So let's start with probability. So clearly, most of you will have a feeling that there is a sort of as long as we can somehow control randomness or domesticate it, take advantage of it, is a very useful tool. And if you think that people have problems with understanding quantum physics, I think people, for a long period of time, even today, there's a debate about the proper understanding of the nature of randomness and the probability theory. For a long time, in fact, mathematicians didn't even pay attention to probability because it was a little bit messy subject and it was not clearly defined, and there were various possible interpretations. And you can see here, I pick up 4 people here that, from Laplace, this says, it's a subjective thing. Then from Mises says, well, maybe those are objective things that are related to frequencies, and Definetti, who may say, well, it's subjective, and Karl Popper, who may say, well, it's objective. So, what exactly it is, this probability thing? How do you really assign a number that something will happen with such and such probability? What is it? So it was, I will not go into details, but what I just say is that at some point, Kolmogorov came in, and in typical mathematical way, you have all those physicists and philosophers discussing, debating what it is, and he says, well, I don't care, I'll define 3 properties, 3 axioms, and I call probability whatever satisfies those axioms. Of course, it doesn't solve any philosophical problems at all, and physicists still, baffled, but how do you make this number assignment? But Kolmogorov basically say, well, anything, I can just make a mathematical structure that, so if you have a dice, you can assign numbers so that you throw 1, 2, 3, and those numbers could be anything as long as they satisfy the 3 conditions. So the probability is a positive number. For example, if I toss a coin, if it is a bias coin, probability could be 1-3 for heads and 2-3, 2/3 for tails, and so they add up to 1. And then there's this sort of the first 2 sort of axioms are kind of trivial, but what is interesting is the 3rd one, which says that basically the probabilities of exclusive events add up. If something can happen in 2 mutually exclusive ways, then we add the probabilities for the whole event, we have the probabilities for for this happening one way and happening the other way. So for example, if I have, say, a symmetric dice and I throw a dice and I ask you, what is the probability of that event that I'll throw an even number? So the way you can calculate it is you say, okay, well, even number, that means throwing 2, 4, and 6. And probability for each probably would be 1/6 if it is symmetric dice. So I add 1/6 plus 1/6 plus 1/6. So that gives me 3/6. So that means half. So this way we calculate probabilities for events that can happen in a mutually exclusive way. Now pay attention to this, because this is actually the crucial point. Now I'm going to tell you something that really will almost introduce quantum physics right away to you. Oh, no, so it seems, this additivity axiom is fine for a mathematician, because you say, well, those are my rules of the game. But the thing is, nature doesn't know about those axioms, really. So nobody told nature about Kolmogorov axioms. And there are phenomena in nature where the third axiom is obviously not satisfied. We want to make statistical predictions in some experiments, and of course the famous double slit experiment is the one that we usually use to demonstrate this. And we can then in this experiment, our naive way of thinking, our classical way of thinking would be to use probability in the way Kolmogorov wanted us to use it. So we just look at, for example, a particle going from a source to some detector somewhere, and you put this double slit thing just to force this particle to take one of the two mutually exclusive ways. So it can go from the source on the left to the detector on the right, taking the upper slit or the lower slits. And you can assign probabilities to each event, say P1 and P2. And the Kolmogorov axiom tells us that the probability that this particle will end up in this detector is P1 plus P2, because those are mutually exclusive events, according to Kolmogorov, and we just add probabilities. Well, okay, fair enough. You go and set up this experiment, and this is not what happens. It turns out that, well, I just messed up my slide a little bit, never mind. So it turns out that this is not the case. It turns out that the probability theory as we know it, classical probability theory, does not give you the right mathematical tools for making predictions in some experiments. So what do? Well, you just think, how to fix it. And, just a long history of how people discovered quantum physics, but the way we understand it today, it is like a different kind of probability theory. So we know how to fix it. And the way we are going to fix it is to use complex numbers, again, back to Cardano, we call them probability amplitudes. And we make connections between those complex numbers with probabilities, but saying that if you want to know the probability, you have to take basically the square, or strictly speaking, the modulus square of the modulus of the complex number. But when you want to calculate probability of mutually exclusive events, you don't add probabilities. You just add those complex numbers, those probability amplitudes. You add those two probability amplitudes, and then you take mod squared of those. And when you do this, and I mean, it's a very simple algebra that you can do the calculations, and you will see that indeed you have the kind of three terms. You have P1 and P2, they appear there, so this is like a classical part of the story. And then you have a correction that comes from the fact that this physicists call it, or everyone calls it, the interference term. So you can see that this interference term depends on what, the complex number can be always represented as a modulus and a phase factor, and those phases, which I here call theta 1 and theta 2, this interference depends on the cause of the difference between those phases. And even this equation is very puzzling, because you may say, well, it depends on the difference. How does the particle know the difference? How does it know what is the phase on the other path? So some people say, well, maybe actually those two events are not mutually exclusive. Maybe this particle in some mysterious way goes through the Bose slits at the same time. So somehow, the particle reacts or acts as if it was sort of sniffing one path and the other path. And and the other thing that is very important for understanding quantum computation is that this term here, this cos, can be either positive or negative. The cos goes from -1 to 1. So you can then, if you look at the black part, P1 plus P2, so the interference term can either enhance the probability that this particle will go to this detector, or can suppress it. So if you have a positive interference, that is when this term is positive, then it is more likely that the particle will end up in this particular detector. But if it is a negative, then the chances are lower. So now, basically, I can then tell you that quantum computing is like a huge multi-particle quantum interference. So you prepare input is like, setting up the initial condition, and your quantum computer is a complex system, but of course it goes through a number of different computational paths, and it just can end up in different outputs. And the art of quantum computing is really to design quantum interference in such a way that you enhance probabilities in the direction of correct answers to your computation. So the chances that you get the right answer, the output that is the answer to your problem, is amplified by the interference term. So this is exactly where the difference between classical and quantum computing comes from. If you want to point it into one particular expression in physics, that the quantum theory really differs from probability by this extra interference term. So things are indeed a little bit different in quantum physics. So now, do we see this quantum interference? Yes, we do. People, use all kinds of experiments, and you can do it with photons. You can see this interference with neutrons, with atoms, with ions. You just force them to take different paths, and then you can see that somehow this quantum interference works. And you can just usually in quantum information science we come up with this sort of generic diagram. So we use, instead of telling you how this interference works for neutrons, how it works for photons, and so on and so forth, we just usually go into simple units, and we call them quantum bits or qubits, and we simply I think I just can I go back with some? Yeah. Well, so we just use we want to go to the higher level of abstractions and simply talk about quantum interference as a sequence of elementary operations performed on some quantum system as a qubit. And the typical sequences that you can see on the top here, those yellow boxes are known as the Hadamard transform, whatever that means. And then in between there is this phase shift. And it turns out, that you saw before that this quantum interference depends on the difference in sort of a phase setting for those two complex numbers. And it turns out that this phase setting, or the difference, can be generated with a number of interesting physical phenomena. And the whole interference pattern, the difference in probability So the difference whether this detector will click or some other detector will click is very, very sensitive to this phase difference, which is a good thing and a bad thing. It's a good thing because you can use it for very sensitive detectors. So even if you just forget about quantum computers for a moment, you can use this kind of phase setting, depending on what is the physical mechanism behind it, to detect and to detect something about the physics that generates this phase difference. So it could be gravitational field, it could be rotation, it could be, we can have very precise atomic clocks based on this interference thing. You name it. So there's a whole area of quantum metrology where you build very sensitive detectors simply because you are able to pick up the tiny phase difference introduced by a certain physical phenomenon and use quantum interference to detect it. You can also use those quantum phenomena, this sort of idea that maybe in this quantum interference, when the particle goes through from the source to the detector, maybe it isn't. Maybe those two slits somehow are not mutually exclusive gateways to the detector. Maybe it is indeed the case that the particle somehow goes through both. And technical word for this, we may say that at this point the particle may be in a superposition of being at the first slit or the second slit. And this notion of superposition allows us to construct quantum operations that do not have classical counterpart, quantum logic gates that don't have classical counterpart. So one, for example, would be the square root of naught. So think about it this way. The basic logical operations on a single bit, right? So you can, basically there are 4 of them. You take your input and you don't do anything, so that's identity. So 0 goes to 0, 1 goes to 1. Or you can negate your input. So 0 goes to 1 and 1 goes to 0. Or you can have, whatever comes in, the output is always fixed at 0, or whatever you put at the input, the output can be fixed at 1. So you have 4 single-bit logic gates, and you don't have more. But then if I give you the following puzzle. So can you think about the logic gate such that think about it as a black box, so that when it acts on bit, and you take another one and put them in a sequence, so that a sequence of 2 identical independent logic gates together generates the operation logical naught. Then you think for a moment. So I call this gate the square root of naught. So you think for a moment and say, well, no, neither of those 4 gates that I mentioned would do the job. So you say, well, no, it's not possible. And as a logician, you say, well, it's absolutely impossible. You don't have such a thing. But in fact, you do. If you can use quantum phenomena, this superposition, you have an operation which takes whatever input you have, put it in some kind of a superposition of 0 and 1, and also can bring this superposition back. So the first gate, square root of naught, can prepare the superposition, and the other one can close it in such a way that it just works all together as a logical knot. So it's and also you can design more complex logic gate. So another way of looking at quantum computing is just sort of use those logic gates that are somehow different, somehow they don't have classical counterpart. They can be implemented. I will not go into details, but it's interesting at the very beginning of this field, when physicists started talking to computer scientists and even to logicians, you would ask, someone, your colleague, your logician, so do you really do you believe that there's such a thing like the square root of naught? And they would be very uncomfortable because there's no mathematical proof for that, right? But then you have a physicist, and here I'm just this is an imaginary conversation between Alan Turing and my supervisor David Deutsch, who was one of the pioneers of this field back in the in the 80s. So David could I could easily imagine him giving this answer to Alan Turing. You have to accept that there is a square root of naught operation because we have a faithful representation of this operation in physics. So I can really just design experiment where I have one box, identical box. A quantum bit comes in, only two states, 0 or 1, and acting together, those two gates generates logical knot. So we somehow, another way of looking at quantum computing is that we take all those impossible gates and we put them together into some kind of a circuit, and we use those square root of knots, square root of swaps, and a few other gates to create, in fact, this huge quantum interference that I was telling you about. So yet another, perhaps, way of telling you about quantum computations. I keep on repeating myself, but I just, maybe if you take home at least 1 point, where is the difference between classical and quantum, then I'll be very happy. So let me just repeat it in similar, slightly different way. So if you think about classical deterministic computation, you think about a machine that goes, from one configuration, from input, and goes click, click, click through different configurations until it stops at the output. Then we can think about slightly, possibly more powerful computation, which is randomized computation. Some algorithms are based on randomness, and they're quite powerful. We use the Monte Carlo methods and all kinds of things. So we allow this computer, the classical probabilistic computer, is allowed to make random steps and go take this computational path or this computational path. But then, in this game, we use classical probability theory to understand this extra power of randomized computation. So we add up probabilities, right? And then here comes the quantum computing, which is a little bit like probabilistic, except it relies on those quantum phenomena of interference, and the probabilities are computed in a very different way. So the good thing about this quantum interference, this phase thing that I was telling you about, is that it's very sensitive in a way that tiny change in this phase shift will generate difference in probabilities, which is basically good because we use it as a detector. It's a very sensitive device. But it's also a problem because when you cannot design the system in such a way that it only interacts with what you want it to interact, it interacts with everything else, and this phase jitters, and therefore this is the phenomenon we call decoherence. So if you cannot keep this phase fixed, this cos function that you saw before rapidly fluctuates between +1 and -1. Basically, it averages to 0, and then you have addition of probabilities. So you recover the classical computation in this particular way. So this is the process known as decoherence, and this is a big thing. So on one way, we have powerful devices with a possible, and again, think about a big quantum interference. That's what it is. We give it computational meaning. And they could be more powerful. And the question is, now, of course, we have to address the question, what does it mean to be more powerful? Well, as it happens, computer scientists had a way of classifying problems into classes. They call it complexity classes. So some of those problems are considered easy and some of them are difficult. And basically, the way you classify a problem is that you look, you pick up a problem, then you pick up an algorithm you have to solve this problem, and then you ask yourself, how good is my algorithm? So one way to test how good it is you ask this algorithm to solve the problem, the same problem, but you increase the size of the input. So for example, you have multiplication, you multiply two one-digit numbers, and then to two-digit numbers, to three-digit numbers, and then you plot the diagram and you see how the execution time or the number of operation grows as the function of the size of the input. And if it grows like any polynomial function, then you say, well, it's easy, it's kind of good algorithm, I can handle it. But if it grows exponentially fast, then it's not good. So you call it difficult. And so there are some problems for which we have good, efficient polynomial time algorithm. And there are problems where we don't know whether we have polynomial time algorithm. People are working hard to find them, and sometimes you know, there are problems where we simply don't know how. We have exponential algorithms, so we call those problems difficult, and we don't even know whether there is an easy efficient algorithm to solve such a problem. For example, factoring is a good example. It's a reverse of, you know, operation to multiplication. If I tell you what are the factors of 15, then you say, well, 3 times 5. 3 is a prime number, 5 is a prime number, 3 times 5 is 15. But if I increase the size, if I give you a huge number, then it will take you exponentially, you will have to spend more and more time to be able to answer this question, and not only you, any computer, any device. So defining the difficulty as a scaling property makes it device independent. So it doesn't really, you know, if you have a factoring is equally difficult for a super-duper computer as it is for your calculator. There is, you know, a constant factor that, you know, that is the clock speed, but, you know, is exponential in both cases. So there's also a class, you know, problems called NP, which are problems which are difficult, but once you have the solution, you can at least check in polynomial time that the solution is correct. Not all the problems have this property. Factoring has, right? So if you may work very hard to find the 2 prime factors, but once you have them, you can at least verify very quickly that you have the right answer. So this is the way computer scientists classify the problem. And when I say then that the quantum computers are more powerful, what I really mean is that quantum computers change those complexity classes. So, for example, factoring is easy for quantum computers because we have a polynomial time algorithm to solve those problems. And you see, what is important that you understand is not the technology per se that makes this possible. It's not because we have a, you know, better technology that we can do. Technology can change rescale it by a constant factor. So it's not going to change exponential into polynomial behavior if you multiply by a constant factor. So the only way to make difficult problem easy to find efficient algorithms is to either use your creativity and find a way of doing it, but you know, the reason we can do it with quantum computers in some cases and we don't find a way to do it with classical computers is that quantum computers have a different set of instructions, a larger set of instructions. A quantum computer, because of this sort of interference, can accept instructions such as, and now take a superposition of 15 and 42, for example. You know? So this instruction makes sense to a quantum computer. So having this extra set of instructions, we can construct new algorithms that do not have any classical counterpart. And this is actually the power of quantum computation. It comes from the fact that now we are able to domesticate this interference by you know, dividing it into those quantum logic gates, the simple steps, and each step is inherently quantum, doesn't have classical counterpart. So then we have to still use our creativity to find good algorithm, but this is basically how it works. One can, of course, speculate about many things, like impact of, for example, of quantum computing on mathematics. So here is one hypothetical scenario. So imagine that you have a mathematical problem, a proposition that you want to prove, and you want to know whether this is true or not. And you know that basically you can do it if you analyze a certain number of cases. But at the same time, there's no computer in the known universe, classical computer, that can do it, because those number of cases is huge. say it's equal to the number of atoms in the whole universe. But, you know, the quantum machine can do it for you. So you can, in principle, you know, you can design a proof that would just take a quantum machine and will just allow you to go into those superpositions. And we can easily create a number of superpositions equal to the number of atoms in the universe. So those are relatively easy things to do with quantum bits. And then through this huge quantum interference that we cannot really terminate at any point, we have to just wait for this to come back to the sort of output. And the quantum computer, you know, goes for a while and says, well, the answer is yes, this proposition is true. Now, here we have a very interesting situation because we have a kind of mathematical proof, but there's no physical record of this proof. Usually when a mathematician comes to you and says, prove it to me, that means, you know, he or she will expect you to go to a whiteboard or write something on a piece of paper and says, okay, we start with the axioms, and then we have this, and we have this, and we have this. You agree? Yes, I agree. And here is the answer. You know, QED, I proved it. So then a bunch of mathematicians can go and look into this and say, well, yeah, maybe there's an error, yeah, I can correct it. So, but this physical proof is an essential part, at least in traditional mathematics, right? So you expect this kind of things. But here, we cannot produce a physical proof. We have a physical process. So are you prepared to put your trust into physical process rather than inspect a physical record to be able to believe that this proposition is true or not? It's interesting, you know, to ask mathematicians, and they are kind of divided. You know, they say, "Well, I would never accept this kind of things. You know, it just, you know, it doesn't work. If you cannot just write it on a piece of paper, or if it is not something that you can, in principle, produce a physical record, then how can I accept this as a valid proof? Because at this point, in order to accept this mathematical truth, you have to somehow put your belief in quantum theory. Because, you know, I explain to you how it works. I tell you about quantum physics. And then, you know, this black box, input comes in, goes, the output is yes. So it's actually interesting. Until today, mathematicians are very much divided whether this is a valid mathematical proof or not. But, you know, it's quantum computers at least may actually come to this point where mathematicians will have to debate. At the moment, you know, I gave you a hypothetical scenario, but it can happen for real. Now, then we come to the questions about can we then sort of, apart from demonstrating simple quantum interference, can we scale up and build quantum computers? The answer is basically yes. There's no reason, there's no law that tells us that it's not possible, so therefore it has to be possible. How exactly they will look like, it's still not clear. There are many possible quantum technologies on the agenda, from trap ions to you know, superconducting circuits, and all kinds of things are being considered at the moment. So it's very difficult to say which particular technology will be the winner. And you know, you may as well say, you know, that if quantum computing is so cool and so good, and you can see some advantage in quantum computing, maybe nature already figured this out. You know, maybe there are interesting quantum phenomena based on quantum interference in nature, which gives you some kind of evolutionary advantage. Well, maybe it's worth, instead of building computers, maybe you could just look for quantum computers somewhere in nature. Well, we don't have many examples of that, but there's at least one. So there's one example where we have a case of the energy transfer in purple bacteria. So there are bacteria that live in a sort of very dark environment at the bottom of the lakes. There are not so many photons getting there. So therefore, those bacteria have to be very, very efficient in grabbing a photon and transferring energy from the photon to the chemical reaction center in this bacteria. And in this process of the energy transfer from light harvesting antenna to this chemical reaction center, we now have evidence that the quantum interference is used to boost, to sort of channel the energy in the right direction, to amplify the probability that will happen. A very simple example, not really quantum computing, but nonetheless a coherent quantum phenomenon discovered. Whether we can discover more, difficult to say. So now the last part, maybe I should just mention something about problems with building quantum computers. I told you about decoherence. Again, mathematically speaking, this interference term is something that you are happy about because, you know, this gives you advantage, but also it's very, very fragile. Any sort of uncontrolled interaction with the environment, this cost factor goes up and down from -1 to 1, goes to 0. You lose quantum effects. So you're back into classical computing. Can we really control it to the point where we can scale up? Because, you know, this decoherence actually becomes more and more conspicuous if you have more and more subsystems. It just, that's why we live in a classical world to some extent. You know, we are sort of a complex entities, and this interference is washed out pretty much. Now, but we discovered actually pretty early that you can not only work against decoherence by designing experiments where you nicely isolate your system. You can never really perfectly isolate, so that's a problem. So but you know, there are better ways, and we can use quantum error corrections to, or equivalent of quantum error correction, all kind of techniques to stabilize computation. And we also have an interesting result which says, you know, up to a point, it will be difficult to scale up. But once you reach a certain level of complexity, it's called a threshold theorem, then it will be easy. So to scale up, you have to build your units with sufficient precision to be able to get into this, you know, magic number. I wish it were 42, but it's not. It's somewhere around it. You know, depends really on the technology used and so on and so forth. So how should you understand? Probably the best analogy I could think about comes from architecture, right? So try to think about building an arch, right? It's not, if you look at the history of architecture and how people got there, it was not trivial. You know, if you look at the Greek beautiful temples, as beautiful as they are, they're not very sophisticated. The Greeks couldn't cover the huge area simply because they didn't know how to build arches or domes. It's only Etruscans came up with this idea, and you know, so you have, you put your bricks or stones, and you know, you can see it's not easy, right? Because if at some point, you know, probably all those bricks will fall down, you have to put this sort of a key stone at the top, and then it will become stable out of the sudden, and then you can construct and build up. You know, once you have arch, you can start building domes and whatever. But to get there, to this point where you have the stability, requires lots of effort where probably, you know, the whole things will collapse many times. So think about this threshold theorem in quantum computing in the same way. We kind of, you know, trying to build the arch. And so we are at the level of, you know, basic blocks. So most in the labs, we can do all those kind of things. To be stable fault, so with building those basic blocks, we try to make those quantum logic gates as good as possible, as precise as possible, because it's like having high quality bricks for building your arch. You know, slightly maybe slanted and adjusted to what you want to achieve. And we are getting to the situations where we want to close this arch and have something that's sort of a fault-tolerant, stable unit, where quantum error correction is designed in such a clever way that even though there's some overhead, there's some little bit more computation, but it corrects itself in some nice way. And then, you know, it's still a way to go. You know, so it's so we are somewhere to the left, I would say, at the arch level. We're still far away from building beautiful buildings like, you know, Hagia Sophia or whatever you see there. And so, you know, that's basically a kind of story that I wanted to tell you. So if there's one take-home message, it's all about quantum interference, quantum interference, quantum interference, quantum interference. You know, it's about what is it? What quantum theory today is just like a different probability theory. It's just we calculate probabilities in a different way because we discovered that somehow nature doesn't know about classical probability theory. It it's successful, it's useful, but there are phenomena in nature where basically the classical probability, especially this additivity axiom, this one doesn't work. So we have to go one level down, complex numbers, probability amplitudes, calculate probabilities, but then we also over time learn how to take advantage of the whole thing. And discovering this new quantum phenomenon was fantastic, because then we can enhance probabilities in quantum computing, build computational machines which sort of deliver. But you know, the same term, this quantum interference term that gives you this power, is also a source of problems, decoherence. And then I try to tell you how to handle decoherence. So let me end up with this puzzle, but probably most of you probably know about it. It's supposed to illustrate the main point that, you know, what sometimes when you discover something new or you take into account something that allows you to solve, if you discover a little bit of new physics or you understand a little bit more about physics, it allows you to solve problems that you cannot solve in otherwise. So I'll give you the answer to this, but I like this puzzle. I usually give it to my students sometimes at interviews to see who is more, who would be a good experimental physicist or who would be good at theoretical physicist. So if you don't know this puzzle, if you have a problem to solve it before I tell you the solution, that means you are probably a logician or a mathematician. But if you see the solution right away, most likely you're an engineer. So the puzzle goes like this. There's this guy here, and you know, and there are two rooms, one on the right, one on the left. In the room on the right, there are sort of 3 electric switches, initially all in position off, and they're connected with wires. It's one-to-one correspondence to light bulbs, which are in the room on the left. You don't know what is this one-to-one correspondence. And the rule is that you are allowed to go to each room only once. Once you leave the room, you cannot go back to the same room. And your task is to figure out what is this one-to-one correspondence. So is it possible? Well, if you're a mathematically minded person, you say, well, no. And the reason for that is I can prove it to you, because if you go to the first room, and it only makes sense to go to the room on the right first with the switches, and then you put one switch in position on and you go to the other room, you see that one light bulb is on, but there's ambiguity about the other 2 that are off, right? Or if you go to the room on the right and put 2 switches in position on, then the 2 light bulbs will be on, and there's ambiguity about this one-to-one correspondence when those 2 are concerned. So you can come up even with more sophisticated argument, and you can say, well, I can prove to you. It's not possible. But then, if you're an engineer, you say, well, it's easy. All you do is, of course, go to the room on the right where the switches are, put one switch, say the first one in position on, go to the second switch, put it in position on, say for 10 minutes, switch it off. Go quickly to the other room, one light bulb is on, one is still warm, right? And the other one is off. So you see that, you know, what happened here is that if you have a very abstract model of computation, if you think about it in a mathematical way, abstraction is a very powerful tool, but sometimes it's just too narrow. It doesn't give you the whole richness of things you can do. So when physicists sort of entered the game and started looking at computation in physical terms, especially if they look into quantum physics, so discovering this quantum phenomena is like discovering this heat dissipation in this case. You know, say, oh yeah, you know, I have quantum interference, so it's a physical process, maybe I can use it. So therefore, you know, you discover out of the sudden that there are problems that you cannot solve if you are confined to the abstract classical model of computation. But if you think about it as a physical process and you include physical phenomena involved, then you can do it. So thank you very much.
Thank you very much, Artur. I'm going to crack straight on so that we might just have time for a question or 2 at the end, but we'll see how we go. Can we ever build quantum cathedrals? Harry.
Oh, yes. Hello. Let's get some water. So that was nice, Artur. Actually, this light thing nowadays doesn't work anymore because we have LED lights and they don't get warm. Okay, so it's a really great honor to be here at this historical place. And I wanted to tell you about the quantum computers that are coming and the quantum revolution that is upon us. And in doing so, let's start with a little thought experiment. Actually, you may close your eyes if you're tired or if you had enough. So imagine that you are in the distant future and you just bought your very first quantum computer online. You're eagerly waiting, and a few weeks later, a big black box arrives at your doorstep, and it says quantum computer, so everything is good. And then doubt set in because actually maybe this was an impulsive buy, and actually it wasn't that cheap. And of course, the very first thing that comes to your mind is, what on earth am I going to do with this machine? And so you quickly start Googling and you find the Wikipedia pages. And as it turns out, programming a quantum computer is actually not at all that easy, and it's actually completely different than programming a normal computer. And actually, maybe even more important, finding problems that you can run on that machine are also hard to find. It's a formidable task. And actually, buying a quantum computer online is not at all that strange. It is still in the future, but small quantum computers, as Artur also explained, with 10 to 20 qubits already exists, and slightly larger ones of 50 to 100 qubits are coming very soon, or are perhaps already there. Big industry is investing into building them, and indeed with somewhere between 50 and 100 qubits, although it sounds like not too much, these machines are potentially capable of performing computations that cannot be performed by even the biggest supercomputers that we have nowadays. But before I venture on, I have to say a little bit also about quantum physics, and Artur already said a lot, and I will repeat a lot. I hope that's okay. For those who are not on the same page yet, it's not about quantum touch. That's something completely different. Also, quantum healing is not what I'm going to talk about. And it's also not an old James Bond movie. No, it's none of that. It's about this theory that was developed in the last century. And you see here an illustrious company of people with famous names as Einstein and Lorentz, Heisenberg, Pauli, Schrödinger. And they were all debating and exploring quantum mechanics, quantum physics. And quantum physics was actually very counterintuitive. Niels Bohr said, if quantum physics hasn't profoundly shocked you, you haven't understood it yet. Albert Einstein said, God does not play dice. And Richard Feynman, someone who's also very much into quantum computing, as we will see later on, said, I think I can safely say that nobody understands quantum physics. So it's kind of a controversial topic, at least then. And I think it's good to explore quantum physics by 3 principles. And with these 3 principles, I can explain a lot of how quantum computers work. And in a way, Artur also touched upon these principles, at least certainly the first 2. So let's dive in. The first one is the principle of superposition that says that an object can be in different states at the same time. So for example, a photon can be at multiple places at the same time. And there's this famous thought experiment of Schrödinger, where he took his cat. Well, he didn't actually do it. It's a real thought experiment, but he put the cat in a box. And in the same box, he put a vial with poison and some radioactive material. And if this material decays, it breaks the vial and the poison comes out and the cat is dead. But when you close the box and you don't look inside, quantum mechanics says that the cat is in a superposition of both being alive and dead at the same time. And this superposition has been experimentally verified over and over with small systems such as photons, and nowadays larger systems can be put into superpositions like molecules. And the idea of quantum computers is that we can even put larger objects like computers in superposition. Of course, there's many jokes about this cat. And at some point, this cat really had enough and is really angry. He's alive and thirsting for revenge. Okay, so let's do a little experiment that demonstrates the superposition. Arthur had it on its slide as well. So imagine you have a source that can shoot photons, and here I have a photon gun that shoots these photons at a semi-permeable mirror called a beam splitter, so the light can go through this mirror or it can be reflected. And when you do so, when you shoot this photon, then quantum physics says that the photon goes into a superposition of going through the mirror and being reflected at the same time. And so this photon actually sits in a superposition on these both positions, very much like the cat you see in the right-hand corner, that's both dead and alive at the same time. And now we have two detectors placed on either side of this little semi-permeable mirror. And these detectors can detect whether a photon is present or not. And when we continue, it turns out that in this case, detector 0 found the photon. And now quantum mechanics, quantum physics says that this superposition state has collapsed by looking at the system. The system has changed and now it has become a definite state, the 0, and the cat is alive. But we could have done this experiment again. And again, we get the superposition. And now when we look, we find that detector 1 clicks. And this is like the cat is dead. And when you do this over and over, you find that 50% of the time detector 0 clicks and about 50% of the time detector 1 clicks. And actually, this is a way of generating random numbers. There's a little box that you can buy. I actually have it in my bag. I'm not sure, maybe I can find it in here. That you can hook up to your computer, and it generates random numbers in precisely this way. Let's see if I can find it. Well, it's a long story. Maybe I find a cat in here. Well, maybe I demonstrate it after the talk. Anyhow, so when you plug it, it's sort of a neat little box. When you connect it to your computer, you get an interface like this. And you can then run it, and you get a bunch of random numbers that come out of here. And by the way, these random numbers you cannot get from your normal computer. From a normal computer, you will always get pseudo-random numbers. But this way, you get truly random numbers out of a quantum mechanical box, out of qubits. So that shows item number 1. You can have superposition of an object in different states. And when you look at it, this collapses. And you get one out of these superpositions, and you see it. And this state has been destroyed. Now moving on to interference, which Artur also said, interference, it's all about that. So let's see how this goes. So here we have again our experiment that we just examined. And a skeptic person might say, well, actually this superposition, that's all nice, but that's of course not happening, because this mirror here, it already determines whether the photon goes through or it's reflected, right? There's no superposition. It might as well just all happen right at this mirror. Now let's go to a slightly more complicated setup called the Mach-Zehnder interferometer, and also Artur had this on his slides. And I think this, I learned the first time of Mach-Zehnder interferometers from your paper, Artur, from the 90s. So you reason classically, let's say, and we say that these beam splitters are 50-50 beam splitters, right? So the photon doesn't go in a superposition, but it really goes through with probability half, or it reflects with probability half. Let's say it works like that. So let's reason. Let's say the photon takes the upper tract. And on either sides here we have real mirrors, right? They really reflect always. So the photon gets reflected, and now it's here. And now what do you think that happens? Well, now we have the same situation as we had in the first experiment, right? We have a photon here that is entering this semi-permeable mirror. And so what happens if you reason classically is that, again, these two detectors on either side, at the end, have to click 50% of the time. This is all as you expect. But now, if you really do the experiment, it's not at all what happens, because you do it, and it turns out that detector 0 always clicks. You never see detector 1 clicking. So it must be the case that these mirrors really behave differently. And indeed, quantum physics tells you get the superposition. And now, at this point in time, interference happens, and you can mathematically make this precise, in such a way that you will only see the photon that goes to detector 0. And never you see detector 1 clicking. So that gives me item 2, interference of an object in superposition. And then the third one is even more mysterious. It's called entanglement of two systems, and they can get correlated in a certain interesting way. And here I have again my two photon pistols, my guns. And I have a box here, the black box, that is slightly more complicated. So I've made it black so you cannot see what happens inside. But it's really very much like you've seen before. And let's see what happens. So when I shoot my two photons into this little box, they come out. And now I illustrated this with this line in between them, and they are entangled. And that means the following. If I let them shine onto these beam splitters again, they go into superposition, as quantum mechanics says. And again, one of the two detectors goes off. But as you can see, detector 1 clicked on one side, but detector 1 also clicked on the other side. And when you do this again, do it quickly, again we get the superposition, but now both 0 detectors clicked. And when you do this very often, you will find that left and right, always the same detector will click, as if they are somehow linked together. Even if they are very far apart, these two photons are entangled, as we say, and they behave in a cooperative, in a very nice way. And we can make use of that, as we will see later on. So I have these three principles: superposition, and then a collapse if you measure it, if you look at it. We have interference of the superposition, and we have entanglement. And before I go on, I have to say something about my favorite subject, computer science. I'm a computer scientist. And computer science actually was also developed around the same time that quantum mechanics was developed in 1936. And here are the three heroes of computer science: Alan Turing, Alonzo Church, and Emil Post. And I guess Alan Turing is your hero. It's also my hero, but it's certainly your hero, who is probably the most famous of the three. And it also is his name that is attached to a mathematical model of what a computer is. We call it a Turing machine. And it's a mathematical way of reasoning about computation and what you can and also what you cannot do with a computer. And Alan Turing not only developed this notion of a computer, a Turing machine, but he also showed in that same paper from 1936 that there are certain problems that cannot be solved on a computer. And actually the problem that he showed that cannot be solved is the following. It's called the stop problem. And this is something you encounter probably quite often, depending on which operating system you use. You're running some problem on your computer, and suddenly this thing pops up that says, "Please wait." Now, wouldn't it be wonderful if you had a little window in the right-hand corner of your computer that said, after 7 minutes and 20 seconds, this thing will end and give you an answer? Or maybe it says it will never answer and it will never stop, and you know that you can safely terminate this calculation. Well, such a thing cannot be programmed, and it was Alan Turing who showed that it cannot be done. But actually, we're not interested that much in things that can or cannot be done. We're interested in things that can be done quickly. And for example, a problem that can be solved quickly is the problem of finding the shortest route, the shortest path from city A to city B, for example, from Amsterdam to London. And it was Esker Dijkstra, who was a Dutch guy, who in '59 at the Center for Mathematics and Computer Science, where I work, developed an algorithm, an efficient and fast algorithm for solving this task of finding the shortest way. This is important, the shortest way from one point on a map to another point. And we actually use this algorithm quite often these days, because if you have a GPS in your car, then you often, then exactly what the GPS does is it tells you the shortest path from where you are now to where you want to go. And by the way, this Esker Dijkstra, so that nicely connects the two now, won the Turing Award, which is the highest award that you can get in computer science. It's the Nobel Prize for computer science. He's the only Dutchman who did that. And also interesting enough, he was working on this algorithm when there were no computers yet. So I found a nice quote that said, "I became a programming of the mathematical center," that was how the Center for Mathematics and Computer Science was called then, "in March of 1952, and they didn't have computers yet," he says. "They were trying to build them." So he was working on this question, what can you do with computers, before these computers were actually there and people were still trying to make them. And actually, it turns out that there's also many problems for which we don't know whether a fast solution exists. And actually, I find this kind of intriguing if you don't ask the shortest way from Amsterdam to London, but you slightly modify the problem and you ask for the longest way. Seems similar thing. Then actually we have no clue on how to do this efficiently. And of course, I mean, it's not a trick thing where you go from A to B and then from B to A and A to B, right? Because then you can make it very long. So the task is that you can only visit each city once. And then finding the longest way from some point A to point B, we only have exponentially slow computations. And what does this mean, exponentially slow? I think it's best illustrated by the chessboard, where you put on the first tile 1 grain of rice, and then on the next tile, you double the rice that you have. So on the second tile, you get 2 grains of rice, and then on the third tile, you double again, so you get 4 grains of rice, 8, and so on, each time doubling. And you can see that here you already have quite a nice little pile, but when you go all the way to the last tile, to the 64th tile, you have 92 billion ton of rice, which is an almost astronomical amount. And it becomes truly astronomical if you put 6 chessboards next to each other and you would continue doubling. Then on tile number 300, you have 2 to the 300 rice grains, which is more than the number of atoms that you have in the universe. So this grows really very fast. And by the way, you might wonder about this longest path problem. As it turns out, we don't know whether a fast or quick solution exists. And actually, this is one of the biggest unresolved problems in mathematics and computer science. It is one of the 7 Millennium Prize problems that is put forward by the Clay Institute. And it's also called the P versus NP problem. And I would love to tell you more about it, but I don't have time for that. Let's go on. Let's now talk about what quantum computers are. And they really merge these two great revolutions, namely that of quantum physics and that of computer science. And it could have actually been done already in the 30s, but it wasn't. It took much more time. It was in the 80s when Richard Feynman and David Deutsch put these two things together and made rigorous what a quantum computer is. And it's explained probably most easily in the following way. A classical computer has as a basic building block a bit, which is a 0 or a 1. You can view this as this detector which has clicked, 0 or 1. And a quantum computer has a quantum bit, which is a superposition of 0 and 1. And it is like before this photon, which is here in superposition, is measured by this detector. In this case, it's in the superposition of 0 and 1. And that's what you can use in a quantum computer. And you can use this as follows, because you realize that if you have 1 qubit, it can be in a superposition of two things. When you have 2 qubits, it can be in a superposition of 4 states. And when you have 3 qubits, and now you already guessed it, you can have a superposition of 8 states. And you see here this nice exponential explosion happening in front of you, 5 qubits, 32 states, 6. And when you have 300 qubits, it can be in the superposition of this astronomical amount of 2 to the 300 states. And now I ask you to make a little leap of faith with me, and now I'm going to show to you why programming this quantum computer that you bought online is really difficult and different. And it's fundamentally different because of the following. So imagine that you have these 300 qubits in your machine, and you can run this massive parallel computation of 2 to the 300 computations in parallel, and that's the leap I'm asking you to take with me. Then you're rich, right? You can do this massive amount of computation in an instant. But the problem is, how are you going to get the answer out? Right? If you're going to measure it, as we've seen, you destroy this nice superposition, and poof, all this magic disappears, and you see one computation. It's not very good. So what you have to do, and Arthur said it, you have to write a quantum program that uses interference to interfere positively the answer of the computations that you want to see, and to interfere negatively the computations that you don't want to see. I always say it's almost like having noise-canceling headphones, where the noise coming from outside is cancelled with anti-noise in such a way that you can hear the nice music on your phones. And I have another bad message for you. This interference doesn't always work. I mean, there are problems, and I will tell you of a few very soon, for which we know it works, but there are also many problems for which this whole quantum computation doesn't work. So if you read somewhere in the newspaper and it says, with a quantum computer you can exponentially speed up any computation, well, that's false. That's not true. It only works for certain very specific problems, and we are figuring out for which one it helps and for which ones it doesn't help. And we have learned a few tricks, but we need to learn a lot more. So quantum computing and quantum program is really like composing, I think. Like a composer who makes nice music, he may have these sound waves interfere in such a way that they interfere and create beautiful patterns, music. And a quantum programmer uses these qubits and makes them interfere in such a way that they do useful computations for you. So making music, composing, and programming a quantum computer is almost a similar thing. So what can you do with it? So one thing that came on very early, and actually it's actually bad news that you can do this, is you can break a lot of cryptography online. So for example, when you buy this quantum computer at Amazon, you get this nice lock in your browser, right? It says that you have a secure connection with this server. Well, it's not secure anymore when you have a quantum computer. And this was demonstrated by Peter Shor. If you have a quantum computer, you can break a lot of cryptography. Now, you shouldn't panic right away, because luckily there's also quantum cryptography, which was developed by Bennett Brassard and Artur Ekert, sitting over there, that shows that the same quantum mechanical effects can be used to actually give you back again some safe communication. So that's good. Another thing that you can do is you can make communication more efficient. So using this entanglement, which I talked about, and also qubit communication, you can make something that we like to call quantum internet. And this internet you can use to do certain computations and distributed computations more efficiently. And also another application of quantum computers is that of simulating nature itself, right? Nature itself is quantum mechanical, and when you have these molecules, they actually have a quantum mechanical description. And when you try to compute how they move around and how they behave, and you put it in your normal computer, then actually you get an error, because this thing is too large to put in your machine. But when you have a quantum computer, you can actually calculate how these molecules behave. And so simulating quantum chemistry, perhaps making new material designs, perhaps new medicines. This could all be something that could be helped with a quantum computer. And of course, there's lots and lots more that we have no idea what it is. I think it's like being in the 50s when Edgar Dijkstra was developing his shortest path algorithm. It was also a famous quote of the boss of IBM, T.J. Watson, and he said, "I don't see a world market for more than 5 computers." He had no idea what to do with it. And now if I ask you how many computers do you have at home, you probably don't even know how many you have because they sit everywhere. And so computers are everywhere. And we are at the same point in time, I think, with quantum computers where we're starting to build them. We have some idea of what we can do with it, but it's really still open and up in the air what will happen. And there's a lot of progress in actually building these qubits. And here you see a few examples. Arthur also showed some of the paradigms that we have. And I think it's interesting to look at this one where Google announced 50 qubits last year. I don't think I ever saw them, but now, a week ago, they announced already 72 qubits. And so the number of qubits seem to be growing exponentially. And also, actually, a lot of money is being poured into that. So the focus is a lot on the hardware, whereas I think it should be equally on the software. We should also be thinking about what to do with this quantum computer once it's there. And I think it's time to put more effort now into this quantum software. And actually, the problems we're facing are also very formidable. Figuring out nice algorithms and nice applications is not at all easy. And so in light of this, a few years ago, I launched a research center, which I called QSoft. It was a cooperation between Center for Mathematics and the 2 universities in Amsterdam. And also, luckily, last year, we got a reasonable grant from the government, from the Dutch government, to explore this quantum software further. Here you see a nice scheme of the things we do. It really borders on physics. You see that on the top, computer science and mathematics. And the things we're trying to explore here are what can you do with small quantum systems, like the ones that have become available now. Also, what can you do with the larger quantum systems? You see this theme over here. Then this cryptography angle, how can you make the world a safe place again, even if we have a quantum computer? That's another theme. And this purely quantum information science is the fundamental part of quantum computing, and this needs to be nourished as well. So a few of the immediate challenges that I see is this question of what are we going to do with our 10 to 50 qubits, and what are we going to do with the 50 to 100 qubits that are becoming available very soon. And indeed, in between 50 and 100, there lies this point where we might be able to do computations that you cannot do on a classical computer. So that's very interesting. Also, I think it's interesting to make small quantum networks where you can test this quantum crypto and you can do this efficient communication and you can test this entanglement over long distances. And another thing is, and Arthur, it sort of touches also on what you said, how can I verify that my quantum computer actually gave the right answer? Right? For up to 50 qubits, I can still calculate on my normal computer. I need a supercomputer, but okay, I can compute still what it did. But when it is having more than 50 qubits, say 100, I cannot verify anymore what this computer did. And so I need some techniques to do that. And luckily, we have some ideas on doing that, but it really requires a lot of thought on how to do that. Then in the near future, when we have more than 100 qubits, these qubits are really unstable. Arthur also touched on that. There's errors that pop up when you have them. And the nice thing is that when you have a lot of noisy qubits, not too noisy, it has to meet this threshold. But if we have enough of them, then we can use them together to build one stable qubit. So when you have more noisy qubits, not too noisy, you can actually use them to build very stable qubits, which we call logical qubits. And this is something that we can do when we have more than 100 qubits. And then things go on, because then we can do this quantum distributed computing. We can perhaps use it with learning theory. You might have heard of learning theory. We can do that perhaps in a quantum way. Quantum optimization, we can optimize certain functions more efficiently using a quantum computer. Of course, finding new quantum algorithms is something that needs to be done and really is very interesting. And this quantum theorem provers, I think it also touches on the thing that Artur said. You can perhaps do mathematics in a completely new way, and you can solve perhaps problems that we cannot solve nowadays with pen and paper or computers. Finishing up, the social impact is something I think we should all be discussing. Security, etc., are consequences of quantum computers. And not only quantum computers, but computers as well may approach human reasoning abilities, and we have to think about how to deal with that. And I think we need a public debate. It's not something that scientists on their own can do. We will see loss of jobs. For example, self-driving cars are becoming a reality, and that means that a lot of professions that are taking place in cars cannot be performed by humans anymore. It will be computerized. We also have to think about privacy versus safety. This is also a debate that goes on, and I think we really need to think twice before we say safety goes before privacy. And also it will be a debate about ease versus ethics. I mean, we all know the book 1984, Big Brother, and then we were horrified by it, but now everyone is using Facebook as if it is nothing, and Facebook is actually much worse than Big Brother. Okay, so summing up, I think designing quantum software is exciting. It merges two great revolutions, namely that of quantum and of computer science. And there are really endless possibilities. I already alluded to the famous quote of the boss by IBM in the 60s. We are really at the same point in time where we have a vast landscape of possibilities in front of us. So that's really exciting. It's also urgent because medium-sized quantum computers will soon be there. And with these quantum computers, we can address urgent societal needs, like perhaps drug design, energy, security, and all kinds of other things. And I think we're also now at a unique position in time where we can focus on this quantum software here in Europe, and we can fuel a new quantum software industry here in Europe and in the Netherlands as well. Because these quantum computers are there, and we are the leaders at the moment thinking about these problems. So with a new paradigm comes, with a new revolution, also comes a manifesto. So we wrote a quantum software manifesto, which, if you agree with me that it's important to focus on quantum software, you can sign or endorse. And this was written together with people from academia and people from industry. Also, big industry now starts to become interested and supports these kind of actions. Thank you very much.